Put your hand near a loudspeaker playing a 440 Hz A note, and you can feel the cone trembling hundreds of times each second. But the audio cable contains no air pressure, no violin string, no tiny singer trapped inside the box. It carries an electrical voltage that rises and falls in the same pattern as the sound. So here is the mystery. How does a changing electrical signal grab a paper-like cone, shove the surrounding air, and recreate a voice or a bass drum? The answer begins with a remarkably small machine hiding behind that cone. A typical dynamic loudspeaker contains 5 crucial parts: a cone, a voice coil, a permanent magnet, a steel pole piece, and a flexible suspension. The cone is usually paper, plastic, aluminum, or a composite, and its job is to push the air without bending at the wrong frequencies. The voice coil is a cylinder of insulated copper wire, often only 20 to 50 millimeters across. The permanent magnet creates a fixed magnetic field inside a narrow circular gap. The spider and surround keep the coil centered in that gap, because the coil scraping the magnet is the mechanical equivalent of a scream. The amplifier sends alternating current through the voice coil, while the permanent magnet supplies a stationary magnetic field. A current-carrying wire in a magnetic field experiences the Lorentz force, summarized by the rule F equals B times I times L, for a wire at 90 degrees to the field. Reverse the current and the force reverses direction. That is the reveal. The coil does not merely get warm, it is pushed forward and pulled backward by electromagnetism. Because the cone is glued to the coil, every push becomes a cone movement, and every cone movement becomes a pressure change in the air. A 100 Hz sine wave makes the voice coil move forward and backward 100 times per second, producing alternating compressions and rarefactions in the air. Those pressure variations travel through air at about 343 meters per second at 20 degrees Celsius. Your eardrum moves with the arriving pressure wave, and the cochlea converts that movement into nerve signals. A larger voltage usually drives a larger cone excursion, which creates a larger pressure variation and sounds louder. But the waveform matters just as much as amplitude. A complex waveform can preserve the sharp attack of a snare drum or the resonant vowels of a human voice. Now test the mechanism with 2 extremes: a 40 Hz bass note and a 10,000 Hz cymbal overtone. At 40 Hz, one full wave in air is about 8.6 meters long, so a speaker must move substantial air to make that bass feel powerful. At 10,000 Hz, the wavelength is only about 3.4 centimeters, and a heavy 20-centimeter cone cannot reverse direction cleanly enough. That is why speaker systems use crossovers. Low-pass filters feed woofers, high-pass filters feed tweeters, and each driver handles a frequency range suited to its mass and size. Physics refuses the one-size-fits-all fantasy. Practice the full chain with a 1 kHz test tone. A phone or music player creates the signal, an amplifier supplies enough current, the voice coil sits in the magnet gap, and the cone launches 1,000 pressure cycles each second. If the amplifier clips the waveform, its rounded peaks become flattened edges, adding harmonic distortion that can sound harsh. If the coil overheats, copper resistance rises and the speaker becomes less efficient. So reflect on the central trick. Electricity never turns directly into music. Electricity becomes force through the Lorentz force. Force becomes cone motion. Cone motion becomes air pressure. And your auditory system finally calls that moving air music.